Okay, so we're going to deal with what is typically called the multiplication rule in this video. Okay, so we need to get some notation down here. P, A, and B means that we're going to conduct an event that has two trials. In the first trial, A occurs, and in the second trial in the event, or in the procedure, B occurs. Okay, so what is the probability that A happens first, and then B happens? Okay, so we also get this conditional probability statement. Probability in, oops, that's not what I want. I want the other way around. B given A. Oftentimes this is read as probability of B given A. It just means that the probability that B happens given that A has already happened. This is the probability of B happening given that A has already happened. Okay, so this brings us to the actual multiplication rule. And this reads as the probability of A and B is equal to the probability of A times the probability of B given A. So this is the probability of A occurring times the probability of B occurring given that A has already occurred. Now, this rule can be simplified under certain circumstances. I'm going to take a look at that now, and then we're going to move forward to some examples. Okay, so to look at when the multiplication rule can be simplified, we have to look at the difference between independent and dependent events. Okay, so if the occurrence of one event does not affect the other, then we say that they are independent, right? So one occurrence does not affect the other from occurring, then we are independent. Otherwise, in other words, if one event occurring affects the other one occurring, then they are dependent. Okay, so how does this matter? Well, if they are independent, that means that the probability of B occurring given A means that A doesn't matter. So that's the same thing as the probability of B. So if I have independent events, right? So if I have independent events, then the multiplication rule can be written as the probability of A and B is the same as the probability of A times the probability of B. I don't no longer have to have the B given A, because B given A is just B because I have independence. Alright, so we need to talk a little bit about sampling and independence, and then we'll move forward. Okay, so sampling is related to independence. You can either have sampling with replacement, where something can be drawn more than once in the sample, or you have sample without replacement. Okay, so here it's like, if you kind of think about this, like sampling with replacement is like rolling dice. Each time you can get the same numbers every time. Sampling without replacement is more like dealing cards. You can only get the ace of diamonds once. You don't put it back in the deck and then deal it out again. Okay. So If you are replacing things between samples, then we have replacement. If you're not replacing things between samples, we are not replacement. Okay? So if I have replacement, I consider my events to be independent. So in this case, the probability of A and, oh, it should be a capital A there. Probability of A and B is the probability of A times the probability of B. Here, if they are without replacement, then these are considered dependent. And in this case, the probability of A and B is the conditional probability, right? The probability of A times the probability of B given A. Okay, there's an important caveat to this, and it's something that's called the 5% rule. If the sample size, n, is less than or equal to 5% of the size of the population, not 50%, 5% of the population, then I can treat dependent events as though they are independent. Okay, and the independent calculation is much easier because you don't have to calculate a conditional probability, the B given A. You just have to have the probability of B. So we're going to call that the 5% rule, and it comes into play when you have a large population and a small, less than 5% sample. Okay, so we're going to give a couple of examples here. In my first example, I'm going to create a situation where you have 50 drug users who are given a drug test. 44 of them got a positive result, which tells that the test correctly picked up that they are using drugs. 6 of them got a negative test result, so that's a false negative, saying, hey, you were using drugs, but we didn't catch that on the test. Okay. So let's say we're going to sample 2 subjects, and if I do it without replacement, right? Sorry, we're starting with replacement. If I do it with replacement, and I want to know the probability that I am getting the positive, and the first one being positive and the second one being negative. So it's the probability of the first one being positive and the second one being negative. So if I'm with replacement, I can pick the same person twice. Okay, so this is the probability of getting a positive person times the probability of getting a negative person. Because with replacement, I don't have to have the conditional probability here, as these are seen as independent events. Alright, so this comes out as 44 out of 50 times 6 out of 50 works out to be 0.106, which is about 10.6% of the time I get a positive person followed by a negative test result. Okay, so I'm going to do the same experiment, but I'm going to have n equals 2. It's going to select 2 people without replacement. Okay, so if I select them without replacement this time, well, my first selection, the probability, sorry, we're still selecting for the same thing, right? So it's the probability of positive and negative. So I'm going to pull, the first one's going to be positive, the second one's going to be negative, is the probability of positive, and then times the probability of negative given positive. Okay, so let's kind of take a look at what's going on here. Alright, so the probability of this, probability of positive, is still 44 out of 50, But given that I just had a positive and I'm not replacing, right? So this, sorry, I've just had a positive and I'm not replacing. So this times, now there's still 49 people left and 6 of them had a negative result. So this is the probability of negative given that I've had a positive. This works out to be approximately 0.108, just slightly higher at 10.8%. All right, so 2 different systems here of sampling. It gives me 2 slightly different results. They're still fairly close, but I should need to know them. All right, let's do an example where the sample size is small and the population is large. Okay, so sample size is small, population is large. Let's say we're at the airport baggage scales for the New York City various airports at JFK and LaGuardia. Let's say that these airports have 810 scales, so that's a pretty large population. And we, on any given day, have found that 102 of those 810 scales are in fact defective. All right, so we're going to take a sample. We're going to sample 2. We're going to grab 2 scales, and we're going to do it without replacement. Okay, so this should be considered an independent event, but because we have a large population and a small sample, 2 divided by 810 works out to be approximately 0.002, which is less than 5%. So the sample is less than 5% of the population. So I can treat this as independent, which makes it actually slightly easier to calculate. So the probability of having a defective bulb, or sorry, a defective scale and another defective scale is going to be then approximately the problem of having a defective scale times the probability of having a defective scale. This works out quite well for me because I know that both of these are going to be 102 out of 810 times 102 out of 810. So if I look at that, 102 out of 810, 102 out of 810 works out to be roughly 0.0159, which, as we know, is 1.59% of the time. So the way I would get 2 in a row that are defective scales from the entire population is 1.59% of the time. All right, so there's the multiplication rule. The multiplication rule can be used to calculate when you have AND type situations, and the rule varies whether you have independent or dependent events. And if you have a large population with a small sample, we always treat it as though the events are independent.